I've spoken to the guys who brought me this in, and they don't have another one, or at least not one available I can look at to get the value of the various blown resistors, and more importantly what this is. Although we already have the SMD code for this, it just doesn't help us. So I think the best bet here is to reverse engineer this PCB. It's a double-sided PCB, and from that we can create a schematic. And with a schematic we can put a kind of like a placeholder in where this should go. We don't actually know what it is. We could, for example, if we want, just put a transistor in there for now. And once we've done that and made a schematic, the plan is that by looking at the schematic, it will become obvious what type of components these are, i.e. MOSFET, transistor, diodes, okay? So we have a plan there. We'll just have to see if it works out. To do this, I think the easiest way is going to be to unsolder the large components on this side. Now, this capacitor, I can clearly see that nothing connects to it from this side. These two, there's tracks going underneath. The fuse or inductor here, again, nothing's actually going to it from this side. The transformer I need to desolder. And this one I can see underneath, but if it comes off easily, I'll desolder this as well. So I'll take the large components off this side, and then let's see if we can get a good idea of where the tracks are going. In fact, let's see if we will know where the tracks are going. I have the large components unsoldered. I think now we can see where all these tracks are going to. Maybe something, in fact something must go under here. That's soldered there and there. But I can see basically where all this goes now. I could now do this in one of a couple of ways. I could take photographs of either side of this, overlay one on the other in an image processing software. I've done this before on the channel, and I'll link that video. I'm going to do this a slightly different way because it's a fairly small PCB. There's not too many tracks. So let's try another method and see how well this actually works. Okay, so I've taken a photograph of either side of the PCB. I actually did this using the overhead camera on my bench, the one I'm using to record on right now. I wasn't recording, but I had the output of the camera on my screen, and I used the snipping tool. Yeah, so I got them both completely flat, not too much reflection, both the same size, both square. And then the top side, this is the bottom side. The top side, I flipped that. I used photo paint just to flip it horizontally. And you can see now the orientation matches. This method may not work so well on a more complex PCB, and bear in mind this is not going to work totally well if you have internal layers. This is really for dual-sided PCBs. I could have, I had some, have printed this onto a transparency. I don't have any transparency. If I layered that on there, that would be fine. Yes, I could use image editing software to do it that way, as I mentioned before. But with this one, I'm just now going to draw the tracks I can see on this onto this one, because there's not a lot of them, so it doesn't really take me a great deal of time. I think I'll probably use this white pen. Yeah, I can draw the tracks. So I work my way across. There's no tracks at the top end here. So the first one we can see goes from this hole, and we can see the hole. So we know the hole was there. And this track then looks like, and we'll look at the PCB as well as a guide. So we can see that track actually comes down the side of this connector to these 2 points. If you think it might go to this connector as well, we can easily prove or disprove this. One method, just by looking on the other side, and we can see that's the 2 connections, so it doesn't go there. You can shine a light off a torch through as well. It's another way. So I think again we can see it doesn't go there. It's a little bit hard because the actual connector's in the way. You could take that connector off, of course, But another very easy way with this, quickly just grab the multimeter and we'll have a look. So we know where the tracker's going from. It goes from here. This is our connector. Doesn't go there. Doesn't go there. So we know that doesn't go to there. We know it goes to there. Okay. And I can do this for any tracks I'm not totally sure where they go. But this one, now I can see exactly where it goes. Down the side of this connector to here. So we can again draw a line from here up behind here. It doesn't need to follow the exact direction. It just needs to go to the right place. So we can say that comes across here, go that way to there. So that track's done. And I'll just do the same with the remaining tracks on this side. This really shouldn't take too long. So we have one from here to here. We can see the pins of that component. Okay, we can see the pad. So we know we have a track going from here to here and so on. Okay, that took me about 5-10 minutes, no more than that. So you can now see where all the lines are. I started off with white, it wasn't very clear. I then decided to draw red over them, but that pen actually ran out. So we have a couple of red ones mostly and blue. So that's what's connected to what. So from here, we can actually make a schematic. The way I'm going to do this, I'm going to use PCB design software. I'm going to add all the components and I'm going to see where each component connects to, and each of these PCB tracks, which might go through the board to the other side and continue, there's going to be a net. So I'm going to put net names on all of the components. I'm not going to draw any PCB traces or rather wires at the moment. I'm going to get all the components on there and then we'll try to start to lay this out in some sort of sensible manner. Okay. I think to make this really easy, I'll now number these components like R1, R2 and so on, and the same with the capacitors and diodes, so it's easier to relate to what is on the schematic and what we have on the board. Okay, so there we have it. You see all the components have got references now, C1, D1, R16, Q1, Q2 and so on. That's for the components on both sides of the board. I've called this L1 as a coil. I'm not sure exactly what it is. It might be a fuse, but we'll figure it out. So all the components are now marked with references. We can now start to put our schematic together. I'm going to print off one more copy of this without the drawing on top of it. That will make it a bit easier, I think, when we come to do this, because I can actually mark using a different coloured pen on each track as we create a net with it. Okay, I've printed that off again, then the second copy. You can see I've actually added the components to this, reference numbers that were on the other side. This thing I've just marked as being 105. I'm not sure what it actually says on it. 501. Anyway, that's that thing until we figure out what it is. Could be a coil, could be a fuse. We can have a quick look with the meter. And then this thing, D4, that looks like a diode but reads open circuit. So that's this one. So I've just marked this as D4 question mark at the moment. It could be something else, like a diac, I really don't know. But then these would be probably thyristors or triacs if it was. That one reads low resistance. It's not short. Could well be thermistor or something like that. Okay, so L1 could be a thermistor. What have I missed off? The transformer. The transformer then has two windings by the looks of it. Let's have a look. Well, that reads open. Does it read this way? That reads a couple of ohms. This one reads lower. So we have something that looks like a transformer winding here. to here, and another one here. Okay, that's the transformer. I have one more component. That's this thing. So now I've unsoldered it, I can see we have 3 windings on here. You can see we have 1, 2 windings, and that is another winding. It only consists of 1 loop, but it is in fact a winding. So we have another little transformer here. This is probably driving those MOSFETs in some way or other in antiphase, so one switches off at an opposite time to the other one. I think we can probably say that because like this winding from here is going in that direction and this one's going in the opposite direction. But of course that depends on how it's connected on the PCB. So on our drawing it comes in this way round, it goes on from the other side of the board. So we have effectively a coil here, and then we have 2 other coils. I'll just put an extra couple turns on because they have 2 more turns on. So that's what we have there, okay? I guess the transformer, we have to call this T1, and the other little thing with 3 windings, we'll call it T2. I'm now going to create the schematic. To do this, I'm going to use PCB layout and design software. There are quite a number of free ones. I know you guys have various opinions which you prefer to use. It really doesn't matter. Just use whatever suits you. There are a number of free ones you can download. So simply search, or you guys let us know in the comments below which ones you prefer to use or which one you prefer to use, okay? And anybody else, well, just try the recommendations and see what you like the look of. To start the schematic, the first thing I'm going to do is to add the components. I'll start with the resistors first. It doesn't matter, but why not? So I'll put the resistors on the sheet. Now I know from numbering them, I have 23 resistors. So that's what I'm going to do. I'm going to add 23 resistors to my sheet. And there we have them. It doesn't matter where we put these for now. Just leave a bit of space around them because we're going to add nets to them. This tells us where they connect to, okay? You can see that all of the resistors by default have come up as 1K. So I'm actually going to add the values now for all the ones I can actually read the value on the PCB. So to do this, I'm simply going to use these printouts I have. It tells me the reference number. It's probably a little bit blurred on here, but I can just look at the actual PCB itself. So starting with R1, R2, you can see that these are 470, and then the 3 means 3 more zeros. So that's 470,000 or 470k. So you can see the value of those ones. Some of them are fairly easy to read, and some are more difficult. So the ones that I can't read, I will just leave those blank at the moment, the value, okay? So I just click on the value, change the text, 470, okay, it's changed, and so on. This will take me probably 10 minutes or so to add all the components, but this is definitely a necessary step. So I'll get on with that. While I'm doing it, we can have a look at any that are difficult to read and see if we can figure them out. So R3 and R4, these from what I can see are 1 ohm resistors. And they're damaged. So I can put a letter X against it or a question mark or anything else I want. That will still come up on the sheet. That is just to tell me this is one of the damaged components. And I'll do so for anything else I can find that is damaged. Okay, so we do the same with this one. To save me continually change the case, I think I'll actually just change this one to an uppercase X as well. It doesn't matter, and it just saves me having to keep hitting the shift, okay? Right, I'll carry on with the other resistors. I'll let you know again if I find any that I can't read the value. I've almost completed the resistors now. These 2 down here by the MOSFETs are 100 ohms, 100, and no more zeros. Anything I found low value I've tested. This one is actually, if you look, 3 or 9, 0 upside down. You can probably see it better the right way up. The reason I'm sure that is a 3.9 and not a 3.0 is because 3.9 ohms is a standard resistor value, whereas 3 ohms isn't. So I'm sure that is 3.9 ohms. It reads very high resistance. And then we have these. So there's another 3 or 9. This is another, I think, 1 or 0. And again, there's one in parallel with it here as well. So that looks like 1 or 0. I mean, the thing's got a hole blown in it. So I'm going to say 3 or 9, 1 or 0, 1 or 0, because they're in parallel again, like those ones were. Okay. I'm confident enough those are the correct values. So I'll put them on the schematic and I'll also mark them as damaged. And there are all our resistors. So next we'll do capacitors. We have, I can see 8 capacitors. So we'll just add 8 capacitors to our schematic. If you were to make a PCB, you would want the correct footprint so you can fit the capacitor into the holes. I'm not going to actually make PCBs with this, but I am going to show you how to make a PCB with this. So what I will do, however, because these are passing through the board, I will choose a through hole capacitor. I'll just use the same one for all of them for now. So I'm going to search for something like capacitor TH for through hole. Okay, we have lots of through hole capacitors here. You can see that's that type of mounting. That's the electrolytic, in fact. Let's go and find something a bit more generic. So we'll go with that one. Okay, you can see the shape of it. Again, if you were to make a PCB, you would have to measure the capacitors, or at least the spacing on the board, and find some which are the right size. You can see these are mentioned on here. Yeah, you can see the height and the width and so on there. Okay, so I'm going to use that type of capacitor for all of mine. I can literally drag that onto the board and that becomes C1, and I'm going to add the rest of them. 7 capacitors. I think I'll actually just arrange them a little bit more in order for now. And now I will look at the markings on the capacitors and put the values on here. The first one, C1A, is actually an SMD capacitor, and it's also a polarized capacitor. We can see the positive end. This is almost certainly a tantalum capacitor, so I'm going to actually change the symbol to this one so it looks more like an electrolytic or polarized. And this is a 4.7 microfarad 20 volt. So let's get that one on there. So this I will delete. This looks like a tantalum type capacitor to me. So we'll have that. It's gone back to C1 by itself, look. Okay. 4U7, 4.7 microfarads, lowercase u, and 20 volts. I can put this in here as well. Okay, I'll do the same with the other capacitors. If any of them look strange or difficult to read the value, we can do it together. C5 may not be a capacitor at all. This could be a varistor or MOV, effectively to protect against transients or voltage transients. We might be able to tell looking at this one with the multimeter. Although if it is a MOV, it will just read open anyway. It reads a high resistance. That could be a MOV. It's mounted directly across the output of the bridge rectifier. I'll leave it as a capacitor for now, but I'll just put a question mark by that component. So S10, K275, and I'll just put a question mark against it. This one, N33, so 0.33 nanofarads. I'm pretty sure that yellow blob specifies the voltage, but considering it looks okay, I don't really need to know exactly what it is because I don't think it's damaged. That one fairly obvious, 12 nanofarads, J is the tolerance, 100 volts. And this thing, the blue one, is not a capacitor at all, PTC. So this is a positive temperature coefficient thermistor. So C7 is not a capacitor at all. Let's just change that on our schematic, which is this one. So that we can just delete. We could rename this to C7, but I'll just leave it C8. And then I need a PTC. Let me see what I can find. In the end, I went for an NTC. It's basically the same symbol anyway. So we'll have that one. I won't call it U1. I'll call it TH1. It could be whatever we want to call it. And I will change the value to PTC. Again, it's not damaged, so I don't really need to know exactly on the schematic what it is. I just need to know where it goes in the circuit. Right, have a few more components to add, so let's do it. So I have this thing, either a fuse or an inductor. It probably reads okay. I'll just leave it as an inductor. We can see how it looks when the schematic is completed, and I have a few diodes to add. So those are all the components. Some have question marks by them. I'm not sure, like for example, that diode just reads open. There's no markings on it. Okay, this is the other SMD device. In fact, they're both there. That's the package type. Those are the markings. I do not know if they are transistors. These two are short circuit, but I do know they are transistors from the data sheet. We have some diodes. I've put them in as Schottky diodes. I actually have a part number, so we can probably figure that out. But for now, they look like diodes if I test them, so that's what they go on as. And the rest of the components. Oh, there's one missing, which is the transformer. So we need to add the transformer with the extra windings. Let me see if I can find something quite generic like that. Yeah, that's 4 windings on. Oh, that'll do. That looks all right to me. Let's have that one. I'm not too worried about the layout of it, but we'll have one of those. Okay. We can number these pins on the drawing, and we can number them here so we know which pin is which, basically. I'm not sure about these phases. It may become obvious. I think these two are in anti-phase. We will see. Right, so that's every component. Now we need to figure out how they connect up. And because we have photographs and we've drawn all the tracks and we're going to use nets, this is quite easy. Let's do it. To connect our components to the tracks, I'm going to use nets. That means I'm not going to draw wires or lines between the components at the moment. I'll show you on one or two of the short tracks first. In fact, that's the ones I would normally do first, is the shorter ones, and then we can put the longer ones in after. So for example, we can see we have R1 and R2. So one end of R1 connects to one end of R2. That's this line. So I'm going to call the lines in as I go, so I know which ones I've already done. And we'll give this a net name. Let me show you how to do it. And then I'll work my way through all the rest of them and add them. And then we'll try to arrange the schematic into some sort of sensible, readable manner. So here we have R1 and R2. And this is where we add the nets. I normally go to the place menu and then go to net port. We have a net now. You can see this thing here. This is one end of R1, so we can actually drop the net on there. You see, now I have another one, okay? So I'm going to put that one there for now. Let's escape. You'll see now they call net port 1 and net port 2. But to signify that one end of R1 connects to one end of R2, they need to have the same name. So I'll call this one just something simple like N1. Okay. This also will be N1. And that tells the software that these 2 points are connected to each other. I can now, if I like, just drag them away a little bit. You see, I get a green line, so I know I have a connection. With a net, by the way, you must always connect the pointed end to the component. If you connect the other end, it will look like it's connected, but it isn't, okay? What I generally do then, we'll go back to the paper, and now we can look at the other end of R1. You can see it goes to here, to here, to here, and there's actually a track there. We can just look at that on the PCB. I think it's clearer on the PCB. Yeah, so there's a track there. I think that one's okay. Let's just check that with a multimeter. It's slightly iffy. Now is the best time to test. I have my fluke meter back. I have a battery now. Okay, so from here, in fact, that is open circuit, that track. Okay, so we know we need to fix that one. Just make a note of that on there. And we can see that this track also goes to one end of C2. I drew it on this copy. It goes to here, which if we actually look, doesn't go anywhere. I don't really know why it goes out. It doesn't go anywhere. And it goes to one end of the AC in. This is your power in. And it also goes to one end of this, which is the bridge rectifier AC. So we will call this net 2 from the resistor to C1 to the bridge and to the power coming in. So again, I can add that to our schematic just by attaching nets to the ends of those components. I find the easiest way to do this is just to click on one of the existing nets, Control C, go somewhere else, Control V, so we have a copy. Now I need to turn this around. We can do this just by pressing R on the keyboard. We drop it on the other end of R1, and this now is N2. This is a different track, so each track on the PCB is a different net. So we now have N2. We can now copy this one, Control C. Where else does that go to? Well, it goes to one end of C2, which is here. Doesn't really matter which end, we just put it here. Okay, it also goes to one of the AC inputs on the bridge rectifier. I'm dragging the image around by holding in the right mouse button, by the way, and moving. Here is our bridge rectifier. So it goes here, just click here, Control V. Okay, one of the AC inputs. And it goes to one of the terminals of the mains input. I now realise I forgot to put the connectors onto my schematic, but it's not a problem. That will do. It has two connections on. We want two of them. This one we will call mains in, or AC in, whatever we want to call it really. Okay. And the other one we will call 12 volts out. In fact, we can do it down here, Luke. You'll soon find quick ways to get around this. 12 volts out. And we know that N2, this one, Control C, goes to one of the terminals on mains in. Notice these have little wires sticking out. That's the end we need to attach it to. So just click somewhere near here, Control V, rotate a couple of times to get it in line. And this actually attaches here, okay? We can see if it's attached because if we drag it away, we get a green wire. I would do this with all of them to be sure. Okay, and that is N2. Now we go to the next track, N3. If you find it helps you to keep track of where you are, you can also write the numbers on N1, N2. I tend to just connect them up in an orange pen. I know the ones that are connected up are already done. So we have another one here. You can clearly see this is from the other end AC input on the bridge rectifier to here. So again, we just connect a net. We call it N3. One of the net labels goes on the bridge rectifier, one on the thermistor, and so on. So I'll get that done, and then let's see what we end up with. I'm working my way along and through these. Now I notice that this track, or net, which is from this end of the bridge rectifier, this is the positive end. So this is HT plus. This is the positive supply from the mains. We can see it goes to here, it goes down to here, it goes down to here. It also goes to this resistor. So I could call this N whatever, but I'm going to call this one HT plus because I know what it is. And this one I will call hot ground or ground hot G probably or something. Because again, I know what it is. And this will help me, I think, when I come to actually lay out the schematic. So if you do find tracks like that, which you think are more meaningful with a different name, give them a different name. Okay, I've now accounted for every track on there, every connection. I checked a couple with the multimeter. There was one I found which is a bad one. I initially got the order of these the wrong way round because the transistors fit on the opposite way that I assumed they did. I just referred back to the video. So that was fixed. And they're all there. So I think we have every connection. If we look at the schematic, can we call it now? We can see that every component has a net attached to it on every pin. So everything's connected to something. What we need to do now is to arrange this into some sort of sensible order. We can quite happily grab a load of these components. You have to grab by one component, not by a label, otherwise it will go by itself. We can stick all the resistors up here so we've got some space to work. The same with these capacitors. Let's just put them where we can actually work. I'll take the transformer with it. It's just easy. If I've selected some I don't want, I just hold control down and deselect them. Okay. So we have a lot of capacitors there. They can sort of go over here somewhere. And I'll probably have a bit of space now to start laying this out. Okay, so I know we have two switching transistors. I know they're bipolar transistors from the data sheet. We have a transformer with one primary and one secondary. And I also know, because I was putting all the nets on, that these transistors are wired in series. So the emitter of one is connecting to the collector of the other. They're both NPN. And the transformer has just one primary. It's not center tapped or anything. It's just a primary and a secondary. This little transformer is clearly driving these transistors. And I have a primary and two secondaries. But I would imagine that effectively when the current is passing one way through the primary, it will turn one of the transistors on, the base, and when it passes the other one, it will turn the other transistor on. So these will switch alternately. I'm fairly sure of that. We will see. And to do that, the current must be alternating direction in the primary. And the primary is driven by this circuit. I can see it goes into here. So I would expect this is oscillating, switching the transistors. We know there are different part numbers. So one is possibly an NPN, one possibly a PNP. And it's some sort of oscillator that drives an alternating current between the two ends of the primary. That's what I think we're likely to have. So that's a kind of a gut feeling. Obviously, as we start to tidy up the schematic and make it look like a schematic, things may become more obvious. I know where hot ground is. I know a lot of components connect to hot ground. So I'm probably going to start off by arranging all the ones go to hot ground down towards a line which will connect at the bottom of the schematic, and all the ones on HD plus up there at the top of the schematic. And then let's see what we've got in between, and let's see if we can make some sense out of it. Okay, so now I've started to rearrange the components. I've grouped them together. So for example, all the ones that connect to HD plus, I have them here. Okay, the transistor, I know the transistor is going to be somewhere near the output, so I've put it over here. I have the driver transformer. Everything else I've pretty much moved it off the sheet. That's fine. And I've started to lay this out and remove these net names. So we can see here, I've put the thermistor in where it belongs. So this was N4, this was N3, N2, N2. We can see, for example, we have two resistors here, one capacitor. The two resistors N1 and N1. Okay. So we can bring those close to each other. We can now remove these N1s. We can make sure first we don't have any other N1s. The way we can do this, press Ctrl F and we put in here N1. We click on net label and find next. And you can see we have both the N1s here. There isn't anywhere else. Okay, so we can remove these labels now. We don't need them. These nets anymore, so that can go. And we just click on the wire. I can get rid of these short wires now. And then I can click on the end of one of these and drag a wire to the other. So that's my two resistors connected together. We can see then that these 2 points here go to N2. We have another N2 there. Once again, Ctrl F. Any more N2s? N2. Don't forget net label. Find. There's one N2. There's other N2. 3, 4. So there's no more N2s. I have all of them. So I can continue joining components together, join them up again, till we have the correct circuit that we want. Okay. So that's basically how we lay the circuit out. As you can see, I'm starting to get a rough layout with this now. So we can see one of the output transistors comes from HT+. I know it's NPN, it looks the right way round. I've left the label on here, or rather the net. This is the base drive. And we can see we have two emitter resistors, which are in parallel. Yeah, and these are both blown. And look, we can see they go to one end of the primary. This is the little transformer. And then out of the little transformer goes into the primary of the big transformer. Okay, you see there. And I have a number of other components all connected into this N17. So I can see that I have all of them here. If I just keep going find next, it will find each one and then repeat around. Once I get back to the start and I haven't found any that are off the sheet, I know I have them all because all those are actually on the sheet. Yeah, I've got them all. So I can now start to join up all this N17 position with the various connections to the transformers, and we'll start to get a better idea of how this is going to look. I'm getting a little bit further with the layout now. This is the small transformer, the one that drives the switching transistors from what I can see. This is the primary of the main transformer, and if we look we can see that we have one switching transistor here from HT, low value resistors. That's going to one end of the primary. The other end of the primary, net 22, goes to one end of the main transformer primary, and you can see the other end of the main transformer primary goes to N5. And if we have a look, we have N5 on the capacitor here going to ground, and N5 on the same value capacitor going to HT. So this looks very much like the same half bridge topology that we would find on an ATX power supply, where you have two large electrolytics from HT to hot ground, and the junction between the two connects to one end of the primary. Effectively, that end of the primary is held at half the supply voltage, about 160 volts. But in this case, because we don't have a large smoothing capacitor, maybe a bit less than that. And the other end of the transformer switches between HT and hot ground. And we can see one transistor is here. So knowing that that's going to go to these two capacitors across from HT to ground, we can say with certainty that from here we will have, via something or other, our other switching transistor, and this will end up at ground via some other net. So there's probably some more low value resistors like this, but that gives me a good idea of how this is actually going to look. As we can see, the second transistor went exactly where I thought it was going to go, just here. It basically reproduces the circuit around this transistor, we can see that. So this point is one end of the small transformer primary, which goes to the large transformer primary. I've put the secondary in now, you can see that. This then goes to the junction of the two capacitors. There's a couple of resistors here. This may be something to do with starting up the circuit, we will see. This is one of the two SMD transistors that I really don't know if they are transistors, MOSFETs. One could be a double diode. We can see that this one connects at least in one way, the base here, via this resistor to the emitter of this one. That looks like it could be some sort of current sense. We have these two resistors, so all the current passes this way. So maybe that's why the base of that would connect to there, making this some sort of current sensor. But remember, this circuit has to oscillate somehow because these are being driven and there are no ICs. Okay, so I'll carry on. There isn't a huge amount of stuff to put on there, now you can see. And let's see if we can figure out how this actually works. I'm just taking a look now at this component. This is the funny blue thing that I thought probably wasn't a capacitor. We see it here, marked PTC C990. PTC sounds like a positive temperature coefficient thermistor. Okay, let's look for a data sheet using that part number. And this is exactly what I thought it might be, involved with overcurrent protection. That's another good reason why I think that transistor measures the current. Okay, resistance, which I think is a resistance at the reference temperature, is 55 ohms and the minimum is 36.5. So it should read somewhere in this range. That means we can actually test that component as well now. So what does it read? I think it read higher than this when I tested it previously. No, it reads 56, so it's within the sort of reading of its specification. So that looks like it's okay. Okay, guys, so we have a schematic now. It kind of looks sensible. This thick red line I've put here, this is a track. This is actually the junction between the two switching MOSFETs, which also goes via the primary of the little transformer to one end of the primary of the large transformer. The other end, as I expected, goes to these two 330 nanofarad capacitors, which effectively forms an AC voltage divider. Okay, so that's why I've put this in red, just so it's obvious where that point is in the circuit. Now, we have some components we're not sure about, but I don't think we need to exactly understand the full operation of this circuit. What we have to understand is what the mystery components are doing, and from that working out what they should be. So we have this transistor, which I've put as a transistor. This is M8P. According to what I can see on data sheets, this should actually be a MOSFET. We'll come to that in a moment or five. And we have this one also, RA4, which I've marked as a transistor. But again, according to the data sheet, this could well be a double diode with the cathodes common here. So anode to cathode, anode to cathode. That's what the data sheets suggest they are, but it's very difficult with SMD components. The other one we have is this diode, which we don't really know exactly what it is. It's marked with a little red mark at one end, so I've considered that to be the cathode, just a guess. So that's why it's this way round. Another thing I noticed during this is that these two resistors here, this is the emitter of the high side MOSFET, are actually a 3.9 ohm and a 1 ohm in parallel, and then the other two equivalent resistors on the low side, which are here, which are quite obliterated. I thought they were probably both 1 ohm, but I suspect now it's more likely that they're the same value as these. Yeah, that's a guess, so it kind of balances. Just a gut feeling, I suppose, really, that one. So really, we do need to try and figure out what these components are. Let's start with this diode here. This connects to the base of the lower side, not MOSFET, but transistor. Okay. And you can see we have a 100 ohm resistor, base to emitter, the two very low value resistors in parallel, and this goes to ground. So for all intents and purposes, the voltage here, basically, this is ground. pretty much, especially when there's no current flowing. When current flows through these, we will get a voltage drop, and we'll come to that a bit later. I think that's important. But the only way this transistor can switch on is from L drive, okay, or via these resistors here. Now, L drive comes from the secondary of the little switching transformer, and the other end of that connects to ground, so it can't get voltage to switch this on unless it's induced from the primary, okay. There's no voltage coming from here. There is voltage coming down here. This is a 0 ohm resistor, so we can ignore it. We have 200Ks in series, so 200K comes to here. That also provides power to Q2. Okay, you see that as well. And for this to be able to switch this on, that would have to either be a Zener diode or possibly a diac, which is kind of like a bidirectional Zener diode. The reason I say that is because if this end is more positive than this end, this can never conduct. So this can never actually do anything unless this end goes more positive than that end. And because that's been held up towards the HT plus, I don't see how that would ever occur. All this transistor or MOSFET can do effectively is to pull that down to ground by switching on. Yeah, drop the voltage here. It can't put voltage on there. So therefore, I'm confident enough this is either going to be a Zener or a diac. Now, it just reads open circuit at the moment, so I'm rather hoping that is a diac. That's how they would read. We'll test it now. I'll show you how to test one of these. If this is a Zener, we have a problem because we don't know what voltage it is. And we have no way at the moment of finding out. So this is a diac. Okay. Type DB3. I think this is a 32 volt or something similar to that. I think most diacs are that sort of voltage, relatively high. So basically this will read open circuit on a multimeter. If we go to resistance range, it reads open on both directions. Okay, and if we go to diode range, it reads open in both directions. Okay, the only way we can test this is by applying a high enough voltage to switch it on. I normally do this using my LED backlight tester. This will give me a current source at 30 milliamps up to about 320 volts. So it's very good for testing these things. If you have a Zener diode tester or a bench power supply that'll go high enough, or some other way to do it. And if you use a bench power supply, you need to put a resistor in series with this to limit the current. Okay. Then we can test our diac. This thing's a bit nasty. It'll give you quite a zap if you were touching both ends of the probes. Okay, 320. Go across our diac. .4. Okay, so this is effectively a 22 volt diac. Yes, I know it's upside down. Let's turn it around for those of you who are not living in Australia. Okay, go again. 22.3. Okay. So that's how we can test the diac. Now let's look at the one on our PCB, which is here. I'll just unsolder one end of it. Okay, so one end is unsoldered. Right, let's test this one. So once again with the tester, it takes a few seconds to come up, this one by the way. There you go, 325. What do we have across our diac, if anything? Okay, 20. So that is a diac. So that's one mystery solved. The symbol for a diac is like this. Like a back-to-back diode thing, okay. So that is a diac. And we know it's a 20 volt one. Okay. So we know what that component is. And we also actually know it's working, okay. So we don't have to worry about that. How does this work? Well, we know these transistors need to switch alternately to connect this end of the primary of the transformer to HT and ground, okay? That's the first thing we know. The second thing we know for certain is that this supply here, this is not DC. This is the output from the bridge rectifier. So what we have here is this at 100 hertz, because I have 50 hertz mains, okay? So that's what we have there. Well, I've got the pen. Let's just put diac here so we know what this is. Okay, now the power when we switch on, assuming we hear the voltage here is rising up, okay? And falling back to zero, rising and falling. So when the voltage is rising, at some point this needs to switch on. I can see that the drive to the base is coming from here. One end of this winding. The other end of this winding is connected to here. Okay. But the voltage here can't rise up until this is switched on, you would think. But look, we have two 56k resistors here to this point. Also, these capacitors will be charging, so the voltage between the two capacitors will be going up to half of the supply. These resistors are connecting directly to here, so basically whatever voltage is on here going up will be the same here, assuming there's no load on this end. Let's have a look. So from here via this primary, which is just a piece of wire at that sort of frequency, via this primary, via this secondary to H drive. So as the voltage here goes up, the voltage here goes up as well. Okay? And that will turn this transistor on. Once this transistor turns on, the voltage here will rapidly go up to the supply voltage, which is probably still increasing at this point. So I can see how that switches on. That will then put current directly from here through the primary to here. Okay? So more current will flow through the primary. Now at some point this needs to switch off and this needs to switch on. The only way I can see that this switches off is that when the current flows through here, it induces a voltage in the secondary. This end becomes more negative than that end. That end is the emitter, yeah? So the voltage here, as the current flows through here, this goes more negative, which brings the voltage of the base down and switches that off. That's really the best way I can see. But I don't think it's that important, because we know basically what all these components are. But I think that's how it works. Okay, when this one switches off, this one needs to switch on. Now, we can see we have 200k to this point. We have a diac, which we know is a 20 volt diac. So this end of the diac would be 20 volts higher than that end. And that end is effectively connecting to ground here. So this end is basically ground. Now when this diac switches on, which basically means there's more than 20 volts here, because the other end of the diac effectively is connected to ground. So when this diac switches on, it will put voltage on the base of this one. And that, I think, is what turns it on. Okay. Voltage here is probably still rising up. It needs to fall back down again. This one turns on and now it connects this midpoint to ground. Okay, and by doing so it also connects this end of the primary to ground. These capacitors have some charge in these resistors as well, so there is some charge in these capacitors here, which would discharge through the primary, through here, via that transistor to ground. But again, it's not totally important to understand this, because we know the transistors are short and we know what every other component is. But I'd be interested to know what you guys think. I think I'm close, but perhaps not quite right. Yeah, I'm learning too. So guys, if you can come up with a better explanation of this, that's great. What we really want to know is what this lot does. Now I can see that this device, Q2, emitter or source, I think this may well be a MOSFET, is connected to ground. Okay. And the collector or drain is connected to this end of the diac. So if this transistor is switched off, effectively it isn't there. Yeah, it doesn't do anything. Then this point, the voltage at this point, will basically be dependent on the value of these resistors. Okay, it will rise up until this switch is on. I can also see this bit of a circuit here. The only thing I can see what this is for is to stop this point going more positive than that point. Okay. So effectively, if this end is more positive than there, this diode will conduct and clamp the voltage here to within 0.6 volts of that. Okay. And if this transistor switches on by some method, it will connect this point to ground. So that diode can never switch on if that is switched on. Which means that this transistor cannot switch on if that is switched on. Yeah? I think we can say that much. Whether it's a transistor or whether it is a MOSFET, I'm not totally sure. I think it probably is a MOSFET because the SMD code says it's a MOSFET. Now let's have a look to see how this could switch on. Well, clearly the only way this can switch on is if there was enough voltage on the base or gate to switch it on. Yeah, it has to have voltage on here. How can the voltage get on here? Well, it looks like, as I've drawn it with a transistor in here, that when this diac is conducting, we have a voltage here. Okay, the voltage here, two things. First of all, it can't be more than about 0.6 volts less than the voltage there because base emitter voltage. Okay, so this can only be about 0.6 volts less than that. It could be as high as there or even higher, although I can't see how that would happen, but it can't be more than 0.6 volts less than that. Which means we can work out effectively the voltage here. And the voltage here will be determined by this resistance, the base emitter voltage anyway, and these resistors. And these are the current sensor. The main current flows that way. So the voltage here will increase as the current through here increases. Okay? And when it increases enough, it would turn this transistor on. And to turn this transistor on, this point has to be at least 0.6 volts more than there. And the voltage on here will depend on this voltage divider, roughly 440k against 47k. But bear in mind, in parallel with this is this PTC. And as the temperature here increases, this resistance will also increase. So the voltage here basically is determined by the temperature, the resistance of that. That's what I see, yeah? And this has to be at least 0.6 volts more than there to turn this on. But there's two problems. One, this transistor has no collector supply. It's got no supply to the collector. It has no voltage supply. And 2, if this could turn on, what it would do is it would pull the voltage here on the base down, causing this to turn off, which would cause the diac to pass voltage, and this would stay on. This needs to work the other way around. When there's enough of a voltage across the current sense, that needs to switch off. Okay? And I can see how it would work if we remove this transistor. So let's do it. And while we're at it, let's change this to a MOSFET. Okay, I've updated the schematic. Let's have another look. So what we have now, and this is how I think it works. We have the pulsed DC here, okay? This is the diac. We figured out how this switches on initially. We think we know how this switches here to switch this back off. And we think we know how this one switches on, okay? So this MOSFET, it's obvious that this MOSFET can switch this transistor off by connecting this end of the diac to ground, okay? So that's what it does. When would it do so? Well, it would do so when the voltage here is high enough to make this diode conduct, okay? There's a capacitor here as well, so when that diode does conduct, it'll take a small amount of time for this capacitor to charge up to sufficient voltage to turn the MOSFET on. Okay, once the MOSFET switches on, this point is connected to ground, and this then switches off again. Why doesn't the MOSFET switch back off? Because this capacitor is charged up. It will discharge because we have 22K and 1.5 meg in series, but it would take a little bit of time to do so, okay? What I think this actually does effectively is takes a chunk out of the incoming waveform, this piece, okay, and uses that effectively to drive the transformer, and the size of that chunk will determine the output voltage. Once this switches off, we would have to wait until effectively this one switches back on again and we get another chunk. Whether we get one chunk per half cycle or whether we get lots of slices of this, I don't really exactly know. Okay, depends how fast this operates and how long that takes to discharge there, for example. Now to the other diode. So this one is connected to this point. We have two 220k resistors in series, giving about 440. This is 47k. So the voltage here would be about a tenth of the total voltage, roughly. I actually worked it out for a 220 volt supply. The voltage here would be 20, assuming this isn't here, but this is here. So this PTC is in parallel with this resistor. At room temperature, this is about 55 ohms. So these two in parallel, we don't get 20 volts here. We get a much lower voltage, too low to make this diode conduct anyway. But as this warms up, the voltage here would increase. At a certain point, the resistance of this would be high enough for this to turn this on, taking the voltage off the diac and switching that off. That is maybe some sort of temperature protection. I'm not totally sure because this doesn't seem to be exactly mounted in such a way. I mean, it's not far from the bulb filament, but that seems to be doing something like that. But it sort of makes sense having the two diodes here, because either too much current flowing that way, or when it reaches a certain amount, or when this gets to a certain temperature, we'll switch this on and therefore switch this off. Okay, so I do believe that's what we actually have here. Another reason I think this is a MOSFET is because if it wasn't, this would discharge rapidly, and probably this would kind of like, and if this discharged rapidly, this transistor may switch back on again. That's my gut feeling, and I think it's good enough. Yeah, so I can say with a fair amount of confidence, M8P, and we can look it up, is this one, BSN20. Okay, see it, N-channel MOSFET. And RA4 is this one, BAV70 switching diode, with a common cathode where I thought would be the collector. I think then we have a very good chance of repairing this. I'm reasonably confident, so I'm going to have to order the RA4 and the M8P. I don't have them. It's quite possible the forward voltage drop of the RA4 diodes and the gate threshold voltage of the MOSFET is a little bit important in this circuit. Therefore, I really don't want to put something else in there. I know these types of power supplies can be a bit temperamental, yeah, but the postage is pretty fast at the moment, so I think those parts will be here in a week or two, which means you have a little bit of time, you and you two over there, yeah, and also him sitting over in that corner, have plenty of time to comment. So get in there, guys, down there. Let me know what you think of this video. That's kind of about as far as my knowledge goes, so I'm kind of on the edge of my own knowledge here. I've certainly learned some stuff from this one, which to me makes it well worthwhile doing it, and if we can get it working, that's great. Okay, so I look forward A, to hearing from you, and B, to seeing you all again soon on another Word Electronics Repair video. Ciao for now, guys.